Good morning, everyone. Welcome to the morning breakout session of the 2026 Grand Challenge. So Monday's plenary introduction of this Grand Challenge introduced the scientific motivation and the three science questions of the Grand Challenge, and also the collaboration with NSF and NCAR's ESPAT initiative, Earth system predictability across timescale, and the systems and the team science approach that we are adopting to organize the efforts and activity of this Grand Challenge workshop. This morning, we will continue that conversation through a cross-disciplinary panel discussion and a small group discussion with the goal of identifying community priorities and actionable next steps. So as we discussed on Monday, the ionosphere thermosphere system is continuously driven by forcing from both the sun magnetosphere system and the lower atmosphere. The response depends not only on the forcing itself, but also on the background state and the pathway through which energy and momentum are transferred across the system. Improved predictability therefore requires advances in three areas: better characterization of the driver, better understanding of the system response, and better understanding of the source and the limits of the predictability. And our three science question this guide our three science questions that will guide our today's discussion. And to explore these questions, we will first hear perspectives from a panel of our community members with expertise in observations, modeling, data assimilation, and AI and machine learning. And we will then break into small group discussions focused on three science questions. And finally, we will reconvene and identify key scientific gaps and priority community actions. And we have assembled a cross-disciplinary panel representing observations, modeling, data assimilation, and AI and machine learning to help us think about opportunities, challenges, and future directions for improving space weather predictability. I would like to thank all of our panelists for their time and for contributing their time and expertise. And with that, I hand this session over to Han-Li, who will moderate the panel discussion. Yeah, and Han-Li, please take it over.
Well, thank you, Ling, for this great summary of our the science, motivations for our GC, this Grand Challenge project. And before I call the panelists, maybe the first thing is I want to, in addition to what Ling was saying, I want to hit or maybe zoom in a little bit on one thing, that's the predictability. So as Ling was saying that, it is, the space weather is a very complex system and with many, many different components. And so I think we really want to have a better understanding of the predictability or what really matters for the predictability of each of those components. So that could be, storm time driver and storm time response, and also for quiet time or relatively quiet time space weather, how the internal dynamics would impact the state or for example, the bubble formation. And the other thing, of course, is the model we're going to use, the tools we're going to use for the prediction. What matters there? Maybe the numerics and the resolution, and maybe it's inevitable that we'll need use parameterization. So if we do, how to use parameterization so that it doesn't kind of reduce or negatively impact the predictability. And of course, the initial state for such a system. And of course, the observation data is key there, and how to organize them and in the optimal way to get the best prediction and specification. That's also very important. and also maybe what new observations are needed there. And then the new development of AI and machine learning, maybe that can be used to improve the efficiency and accuracy for all above. How to use that? That's a great thing to think about. The other thing is I think maybe I will encourage the CEDAR community to kind of see or explore the value of CEDAR in this space weather study, because we have a large collection of very high quality observations, ground-based observations, and how to use that most effectively. And the recent studies by NavGen, Jawara, and WACAMAX, they all show that the meteor radar, a network of meteor radar, can have a big impact on the dynamics or the model description of the dynamics in the MLT region. So how to, maybe we can expand that further to include IMCP, the International Meridian Circle Project measurement, Mango Nation, and maybe in the future Dashi, how to engage the people from that community and how to use the data from those observations. And so basically we want to make the full use of all the parts we have, the high quality parts, and make the whole system, the CEDAR observations, work together to improve space weather. So those are questions maybe I'll pose to our panelists, but also the audience, and to encourage every one of us to think and maybe explore opportunities and future ways to to contribute to the space weather study. So without further ado, I will invite our 4 panelists here. I think Nick, is Nick here? Oh, Nick Patatella from NCAR, Jeff Anderson, also from NCAR, and Asti from SRI, and Ben Martinez to give their perspectives on some of the aspects we just discussed. So I think the order is Nick first, right? You'll talk about your perspective on models.
Yeah, I will give just a brief perspective on sort of modeling, really physics-based modeling, not sort of empirical or other, I think Ben will discuss maybe AI, ML models. So this is really physics-based modeling. First, I think it's useful to understand kind of the recent developments we've had in physics-based modeling in the last, 10 or 15 years. There's really much more mature whole atmosphere models, so surface to exosphere, developed by several different groups now, and then also sort of whole geospace models where you're coupling in magnetosphere to, and these are intended to better capture lower atmosphere and MIT coupling. And of course, there's sort of a linking between those two now with WACAMAX and Gamera as part of the MAGE framework. And then there's, recently there's been a push towards increasing resolution, which is kind of tied into increasing computing power. And then I think, especially in the last few years, we've seen kind of improved numerical schemes being implemented. An example here is moving from a sort of regular latitude-longitude grid to a cube sphere type of grid, where then you no longer have a polar singularity as you sort of increase resolution, and then that allows you to do higher resolution studies and sort of regional refinement. And that comes with better numerics as well, sort of adapting what has been developed in other communities so we can better solve, especially as we push the resolution. So these are some of, I think, the important recent developments. Some of the challenges, I think, that remain, Hanli summarized some of these, but there's still a lot of uncertain model parameters. And these uncertainty in model parameters lead to sort of persistent model biases, I would say. The figure here is from over 10 years ago, where we compared a few different whole atmosphere models that were supposedly simulating the same atmosphere because they were constrained in the lower atmosphere. But if you look at the details, they're very different among the models, which is largely due to how things are parameterized, especially subgrid scale gravity waves. And I think if we did the same comparison today, you would see many of the same biases among the models. These are sort of persistent, and they're not, partly from insufficient observations, but we just don't have a good way to constrain them. So we're seeing, some biases just remain, and that obviously has some impact on the predictability. Computing cost is, of course, still, even though it's getting faster computers, we still try to push the resolution to the limit, so there's some limitation there, and we still have kind of forcing uncertainties, both from lower atmosphere, but also from magnetosphere. So those are still sort of challenges that, I think some of these are also persistent challenges that we will kind of always face. Just in terms of the specific topic for advancing predictability, these are just some of my thoughts in terms of how physics-based modeling can really contribute to this area. I think one of the main areas is really just doing controlled experiments. So one of the advantages of a physics-based model, you can turn on and off different things, and then you can look at what is the sort of driving force of different parts of space weather. We can understand uncertainty and also the sources of uncertainty. So how does some uncertainty in the geomagnetic driver map to uncertainty in, say, thermosphere density or something like that? So that is one other area of understanding. And then looking at predictability, we can look at what is sort of practical prediction skill and where that is coming from, but also kind of theoretical limits of predictability. So at a certain point, you probably can't predict something, and so we should understand what we can and can't do. And then there's a question of actually doing studies to look at what we can and can't predict. I would say currently, but the theoretical limit is also what we should strive for. So we need to understand that just because we can't predict something now, that doesn't mean that it's not predictable. We should understand what we should be able to predict and how we work towards that. But then also maybe what is just unrealistic to predict. And then I think there is a sort of good link between observations and modeling. They can really provide a much broader context for observational studies. So if you have a limited range of observations, then models can give you the sort of broader context of what is happening. And then last point, I think all of these topics are really interconnected, and I think advances in modeling can really benefit data assimilation observations by giving you a better sense of what is happening when you observe something, and then also models can help form the basis for AI and ML. So models are maybe a very model-centric view, but they can really contribute to all of these areas. So that I will pass it to, I think, Asti for.
Thanks, Nick. I think it's a right way of putting it that models and data can inform each other. So I will talk a little bit about what the observations can do or are doing for the space weather predictability. We have two types of models, two types of observations in the world. At the moment, you have something that gives you standalone coverage, precise coverage at a single location versus wider coverage at the less precise measurements. The precise measurements are something like infrared scatter radars that cannot necessarily be made into a wider coverage instrument, but they exist to give precise measurement at a single location. There are a few of them in the world, but not. It doesn't provide wider coverage. Then you have networks which don't give you necessarily precise measurement of a specific quantity, but they can give you wider coverage of dynamics that are going on in the system. We also have the space-based observations, which provide global coverage with asterisks there. But what is the advances that can be made very specifically in our field that we have seen over the years is when you combine the observations from all these separate entities, and we do it intentionally. And so that is something that traditionally hasn't happened in our field. Mostly things become serendipitous discoveries serendipitous collaborations, but not intentional collaboration. So that is something that requires us to work towards. The other way of using the observations optimally is to make sure that the continuously streaming data is used effectively. And by that, I mean that in last decade or so, we have made a lot more progress in making sure that the data are continuously streaming. Not only they are continuously streaming, but they are also getting stored, and that is a big strength. That allows for building nowcasting models, that allows for looking through the historical data for forecasting models. They help us understand day-to-day variability and physical drivers of variability. And so this data are not just, it's not to look at the current data that is coming in right at this moment, but because this data in last 1.5, 2 solar cycles, as we have data from all of these this time that is stored and can be used to build models, not physics-based, but the data assimilation models and other things. The long-term data we have seen in this conference itself, climatological analysis and variability across different geophysical geomagnetic conditions can be derived from a lot of the observations that are already there. Of course, there are gaps, and we have to recognize the gaps for true space weather predictability. The decadal survey has articulated strong needs for what we need for space weather predictability. Thermospheric neutral density is a strong one, and that is a key thing that we have to figure out how to do well at the scale. Ionospheric conductance, gravity wave seeding of irregularities, Joule heating rates, neutral winds. There are the few, this is not an exhaustive list of existing gaps, but these are some of the key ones that we have been discussing and debating for last at least a decade. Hanli mentioned the ground-based networks that we have. Here is a plot of some existing ground-based networks around the world, right? And it's not just networks, but also standalone instruments together. So if you look at this, it looks like a busy thing. That we have so much measurement, so much thing. But each of these things give you different way of looking at the thermosphere, ionosphere, and we have to make the optimal use of using all of this in conjunction with each other and the space-based instruments. And that's the challenge that we have to put our efforts towards. The current technologies that we have, they enable, like I mentioned, continuous streaming and storage of data. It allows us to actually develop networks with COTS components. Gone are the days when we have to build something in our lab and only one of the groups in the world can build it, and then they have to put it. Commercially available technologies can be used to better do all of this things we are trying to do. And we can create infrastructure that is easily upgradable, replaceable. So there is a lot of potential here if we identify exactly what we need. And with that, I'll throw to Jeff.
All right, so I'm Jeff Anderson. I'm a data assimilation scientist, so a little bit of an outsider to this community. However, I like this community. This slide I actually first showed at a CEDAR meeting in 2008 in Midway, Utah. That was a weird meeting, but it was a lot of fun. And I've kind of tried to check in on these meetings about every 5 years. The pandemic messed that up, but this is my fourth meeting.
It's Zermatt.
Zermatt was in Midway, Utah, yes. Yeah, Zermatt's the resort, Midway's the town. So I just want to remind you quickly what data assimilation, in particular ensemble data assimilation is. So basically, as the slide shows, it combines information from prediction models, which we heard about from Nick, and from the observing systems, which we just heard about, and takes the forecasts and the observations, and it uses statistical techniques to attempt to combine the information from those things and produces something that has been historically called in tropospheric prediction and analysis, basically our best estimate at the given time, combining these sources of information. But it can also provide diagnostics that help us learn more about it. And for the full prediction/predictability problem, this is normally applied in some sort of cyclic fashion. You use your analysis as initial conditions. You run a forecast with the prediction model forward in time to when you have more observations. Then you repeat this process of combining them, and you cycle this on through. And so this helps you to incrementally improve and build a series of this. So in the years since 2008, in 2008, data assimilation was really pretty darn new to this community. There were a handful of people that looked at it. I think the last few meetings showed that there's a lot of activity going on in data assimilation with a lot of different models. We've seen talks and posters showing results from reanalyses. The last science talk this morning was using a reanalysis, a data assimilation product. So there's a lot of work that's been going on here. But I think it's very, very difficult in a large community to get it all together. And it's important to remember that data assimilation does more than just provide these analyses. Okay, so in addition to using these forecasts for prediction, they can also identify systematic errors between the model and the observations, so deficiencies in both systems. They can be used to directly estimate model parameters. And in fact, in that 2008 talk, I mentioned trying to estimate F10.7, for instance, which was outside of the model we were using, but using data assimilation in the model to estimate external forces. And we know that these systems, many of them are very strongly forced compared to, say, medium-term tropospheric weather. These things can also be used, data assimilation can also be used as a tool to look at the observing system, to actually design observing systems to evaluate the information available from particular observations. And again, all of this is predicated on having information about the uncertainty and the correlations between different things. And those are most readily addressed with ensemble data assimilation methods. And ensemble means cost. You have to run the model a bunch of times. And so that underlying issue of cost with building a data assimilation system is going to drive a lot of things that come further on in the discussion from the panel. I do want to address a couple of specific things. The first thing is the notion of prediction and predictability. And so I've worked as a data assimilation scientist throughout the past 30 years with a lot of communities in the Earth system. You're not as unique as sometimes it may seem that you're sitting here. So there's many, many other parts of the Earth system that are strongly forced by some other part. There's many parts that have varying time scales that are important for different things. And so there is a lot to be learned from interacting, I think, more closely with other communities. And that's part of what the SPAD initiative at NCAR is trying to do. It's trying to bring together a broader community so that we can share these ideas on what we need to do to deal with some of the challenge in these problems. The other thing I want to point out is to make very clear the distinction between predictability and prediction and how those two things are interacted. So predictability is formally a function of the physical system itself and the observing system. It has nothing to do with a model. We use models as our primary tool to estimate predictability by simulating what goes on in the atmosphere. And again, that would itself be a function of the model and the observing system again. So all of these things are tied very closely together. And I think the key issue that we need to address moving forward for this community is how much resource the CEDAR community and the broader community around it wants to put into formalizing prediction and predictability research. And I think a key point that draws it out at this meeting is, as I said, there's lots of good stuff going on with data assimilation. But there is, compared to many other Earth system meetings similar to this I go to, there's a lot fewer statistics being shown at this meeting. I get that. I'm not criticizing it. We did actually see some nice statistics, again, as an example, in the last talk before the science talk before the break. But it's way less than in other communities. And I think you need to address why is that the case. So one reason it could be the case is just that the uncertainty we have that we're dealing with here, we're just not ready to deal with quantifying it, to evaluate it. But maybe if you're going to do this prediction and predictability, you have to reassess how much resource you want to put into being able to assess uncertainty to more carefully evaluate. And that's where the cost comes in. And so the sacrifices that come into play then is that you can no longer use your available computing resources simply to run the largest, coolest, newest model you can possibly run. Instead, you have to say, I'm going to run a model that is 10% or 2% of the cost of the coolest thing I could run a single version of, and I'm going to have to run multiple instances for this to evaluate uncertainty and ensemble data assimilation. So those are things that really the community needs to address. Where does it want to put those resources? People like me can help you if you want to put more of those resources into predictability and prediction, but that doesn't mean you should do it. It just means you could do it. So thanks.
Hi, everyone. My name is Ben Martinez. So yeah, I'm going to talk about AI and machine learning, which is very much a hot topic right now. It's not exactly a new technology, but it is in its golden age. And it's popular now, as you can see from this chart showing the percentage of AGU abstracts in which the word AI or ML appears. This stops in 2022, but it's clearly trending upwards. And then also in the president's fiscal year budget request to Congress, the first area of interest was artificial intelligence. So that's why, I mean, there's a lot of people are putting AI into their proposals and so on and so forth. So just to get us all on the same page, because this is, as compared to the other things, numerical modeling, data simulation, this is newer sort of to the community. So AI are computational methods that perform tasks requiring pattern recognition. And then machine learning specifically is an AI where you're learning a task by optimizing some loss function. There's supervised learning, in which you learn from a labeled ground truth data set. So that's kind of like when you have a person go in and say, this is this kind of event, and then the machine learns that relationship. And there's unsupervised learning, where you give it data, and then it finds the patterns on its own and classifies them that way. The types of tasks that AI and machine learning are used for is classification, so assigning a label to an event. Identification, determining whether or not a particular event occurred or if it was background noise. And then regression, which is, that's like fitting, encompassing forecasting, emulation, things of that nature. So I just want to highlight a few of the advantages and disadvantages of AI. Start with the advantages. It's very powerful for pattern detection and modeling relationships. And it's very computationally efficient. I think everyone has mentioned so far cost as being a big issue here, and this is one of the areas that AI can contribute a lot to our field, is if we can, replace models or at least aspects of models with emulators of those models. That could, for some purposes, that could bring down the cost of running them, as these models are much cheaper to run. But there are disadvantages to AI. It requires very large data sets for adequate learning, although we do have things like that. It's fundamentally interpolative, not extrapolative. It struggles with events that are outside of what it's actually seen. And then, although it's cheap to run once you've trained it, training it can be quite expensive. And then there's the whole issue of black box modeling, where compared to a numerical physical model, you have the physics in there and you can read it off, but with the AI model, you don't have that, and it's harder to interpret them at times. But then there's in between, when you have this physics-informed neural networks and so on and so forth. So I'm just gonna, I guess, highlight a few like ongoing works in our field for machine learning. So there are emulators being built. For example, I just highlighted two here. There's TiGCM emulators and AI or WACMX emulators. There's also partial emulators that are being worked on, where you emulate part of the atmosphere as opposed to the whole thing, like a boundary condition, to make it cheaper to run without getting rid of all the physics. There's plenty of identification projects. I just showed this one. Acoustic gravity wave identification and phase velocity estimation from all-sky imagers. Then AI is also being used heavily for parameterizations in models, because AI can be more flexible and less strict as like a, by hand parameterization, and it can generalize better than other gravity parameterizations. So that's one way that these models can improve the numerical modeling. And then also there's physics-informed neural networks, which are neural networks that try to operate in the kind of gray box area where there is actual physics informed, you're trying to back physics out of those models. Then there's generative time series forecasting is becoming popular as well. And there's also been efforts to actually use data assimilation assimilating data into machine learning models, which data assimilation is expensive because it requires ensembles, but running an ensemble of a machine learning emulator is much cheaper than it would be for a numerical model. And then, yeah, I guess the only other thing I'll add is So compared to the lower atmosphere, the troposphere, they're using AI and machine learning for forecasting much more than we are, and I think it's very worth it to see what they're doing, what we can adapt to our own field. There are differences, of course. They have much more continuous data, which we don't have, so we rely more on reanalysis to fill in the gaps of our sparse data sets, and yeah, okay, that's all for now.
Thank you, Ben. Now I forget what's the next part of our routine. Oh, that's it. Okay, we'll start. Great. So I guess none of you can really see the screen. I will read the question for you. So the first question is, yes, maybe that's, if it's not too dangerous. I will read it anyway. So space weather prediction, this is prediction, not predictability, requires understanding a highly coupled system spanning the sun, solar wind, magnetosphere, ionosphere, thermosphere, and even interactions with the low atmosphere. So what are the most significant barriers to improving predictability across the coupled system? Anyone want to take that first, or just by order?
Since there's no volunteers, I think that means I will go first. So I think that it probably depends first on what problem you're trying to solve. Different, probably if you're trying to predict different things, what is the sort of main barrier will be different. If you're trying to understand, say, concentric TIDs over the U.S., you probably have a different barrier to your prediction than if you have trying to understand variation during geomagnetic storm. I think some of the barriers, we still have a lot of uncertainty in the forcing, both from the above and below. This is sort of the modeling centric view, but we really don't know, I think, well what the true forcing is, and also how uncertain what we do know it is. So there's a lot of uncertainty there that ultimately translates into down the line what is this sort of prediction ability, and so it creates some barrier there.
Yeah, I think that's an important thing that Nick mentioned about what is it that you're trying to predict. And I'll take his example of, say, concentric waves seen in the TEC or TIDs. So one of the things that we identified here is we want to understand the forcing from below and how it impacts the thermosphere, ionosphere. But I would say one of the barriers is not having observations at a specific quantity. So for example, we have from weather systems, we see all these lower atmospheric forcing events like thunderstorms or hurricanes and things. And then we have TECs, we have even aerial imagers or from the satellite measurements, what's going on in the F region, but we did not know anything about the thermosphere in between, right? So what exactly is happening at that level? I would say that what we don't have is information from strategic locations, both in terms of the layers, atmospheric layers, and in terms of the global coverage but not exactly at every place in the world, but in a strategic location that gives us a window into what is happening at, say, in the suborbital ionosphere, what is happening at polar cap, what is happening in mid-latitude, but at a location that can be extrapolated then into the more broad predictability.
Yeah, okay. Yeah, I mean, I agree with what has been said so far. I think also, boundary conditions and I guess like how nonlinear the system that we're working in is, and then which is one area where machine learning can be very helpful is in finding those nonlinear patterns and translating forecasts that we do have of the of those boundaries and propagating them into our system. Yeah.
Jeff?
So from a data assimilation perspective, this follows on with Nick's thing. So properly assessing and accounting for uncertainty remains the key issue. And that uncertainty comes in a variety of forms. The most obvious one is the uncertainty in things that are external to whatever system you're modeling. And people's systems may be broader or narrower here, but somewhere outside of this, we're probably still getting to something where external forcing is playing a major role. And appropriately characterizing that, and the important thing is to have at least enough uncertainties to span what the real solution is. And so that is still a challenge, both with incoming solar, with stuff from the troposphere. In addition, there's lots of systematic errors with models here, and that's experienced across the Earth system as you move into more of a prediction capability where you have more experience directly confronting models with observation in statistical fashion. You will identify deficiencies in your model, and you will then work on improving them. At this point, I think we're nowhere close to what NWP for the troposphere is in this community, and that the models just haven't had enough time to do all of that, and it's an extremely complex system you all work with. So having methodologies that are able to deal with that uncertainty is important. In some of our work with Nick, for instance, I think the biggest struggle was not getting the DA to start running. It was coming up with the methods that work with the DA to increase uncertainty until it was the right point. And then that brings in one more complexity with the sort of physically based GCMs in this context. The numerics in many of these have been developed to be able to deal with simulations where the model is comfortable. And when you start trying to incorporate observations through data assimilation, in essence, you make the model uncomfortable. You stretch the numerics. And so there are many, many issues with models that are happily running along in their own climate zone, if you will. When you introduce observations, then they immediately become numerically unstable. And so it can require significant work redeveloping numerics, tuning numerical damping, and other things to deal with these issues. Final comment is we've talked about cost, and we heard the AI thing. Having AI as the models for data assimilation is a very, very intriguing idea. So far, that has generally led to problems with that uncertainty thing I led out with, and that is that the AI models tend to produce estimates of deficient uncertainty even compared to the data sets they're trained off. And I think that's a problem that can be solved and maybe solved soon, but still out there.
So if I can add something to hearing after Ben and Jeff, one of the issues that I see pretty regularly is that we do not have a good way to characterize day-to-day variability. And I think from the perspective of instrument provider, where the instruments are generating continuous data, if we do not look at day-to-day variability, we are basically missing important physics, and that plays directly into improving predictability. We think most of our analysis stems from the idea that we should do the long-term analysis, we should do event-based analysis, and so we focus on the explosive events, either from lower atmosphere or the solar storms, but in between that characterization, I think we are missing large chunk of physics.
Mm-hmm. Thanks. Oh,
Yeah, you go ahead.
I think Ben has something.
Yeah. I just wanted to add on top of that. Maybe it's obvious to say, but I think it's worth just saying that like the AI models that we're training are going to inherit all of the issues and biases of the model that they're being trained on and the data that they're being trained on, which it makes it that much important to get things right, because the AI models are much harder. When something's wrong, it's much harder to see why, and then it's almost impossible to correct without retraining, which is an expensive thing. So, yeah.
Thanks.
Yeah, and I just want to say, everybody, if you have an idea, please pitch in, and I will holding the microphone, standing back there, and if you raise the hand, I will see it. Yeah, so a live discussion is highly desired.
Okay. Yes.
So, I mean, I have a comment and a question. So, I mean, the comment is more along the lines, I mean, we are talking about a nonlinear system, right? And I mean, basically from standard physics, I mean, even if you think about a double pendulum, we know the better you know your initial conditions, the longer you get at least some kind of reproducible result, right? I mean, so that means the number of initial conditions, or in other words, how many, and following up what Asti basically said, the number of and coverage of measurements and cadence and so forth is obviously important. So, but I think we also need to think about, I mean, we have a lot of ocean, right? So we can't put a lot of ground-based instruments there. So what kind of space-based observations do we actually need? So 50 CubeSats or 5,000 or 50,000 and these kind of things. And I also like to remind everyone there was quite a bit of discussion on these topics specifically at the Heliophysics 2050 meetings a few years back in terms of initial conditions. And my question is more about, I mean, when we talk about predictability and all the different mechanisms there. So what's actually our target? So are we talking about minutes? So when we talk about more solar magnetospheric stuff, or days, or both, or so what can we actually do?
I think you are talking about prediction, not predictability.
No, it also goes in terms of predictability. So I mean, if all these whole things work together, which they obviously do, right?
Mm-hmm.
So what kind of timescales
You
are
mean
actually
like-
in terms of predictability possible, right?
That's right.
So what are your thoughts about that?
Yeah.
Make a comment. First, to your first point, I think Jeff brought this up a little bit in his slide, that we can use things like data assimilation to understand what we need and where we need it, and I think that's not really a tool that's widely used for, at least geared towards trying to improve prediction. We kind of look at what we can observe and where maybe there's ground infrastructure, and then say, well, that's what we'll do, not what we might ideally want for, say, prediction. And to your second point, when we had some pre-discussion among the panel, this was a question we discussed of what timescale, and I think there's probably different reasons you might want to predict different timescales, and that's probably a broader community discussion of what the focus should be, at least first for this grand challenge, but probably more broadly. People are interested in, say, decadal prediction for satellite lifetime, for example, but that's probably more of a question of, can you predict the solar flux, not the necessarily inherently thermosphere question. But then there's other questions, like you said, shorter timescale. So I think that should be discussed, and what is relevant for different problems, and what are the challenges in each area.
Well, I mean, I think one of the things, if we are able to predict something accurately, that means we understand the physics. And that is sort of the fundamental goal why a lot of us got into science, to understand the natural environment. So if we are able to predict exactly when a solar flare leaves sun, exactly what it does, comes to the earth, exactly what impact it makes, that means we understand exactly the physics behind it. But now we also have other customers who want it for different aspects. So it is important for us to define, I agree with your point, what we are trying to predict and why we are trying to predict it. And the time scales will depend on what we are trying to satisfy at any given moment. But the larger goal of we should be able to, we work towards the predictability of, because we want to understand how the world works, is the, base idea, I say. But yeah, it's an open question, I would say.
Oh,
Okay.
yes, Jeff.
So the use of observing system simulation experiments has been quite broad in some other fields, many funded by NASA. And that's basically, again, using the models and data assimilation to simulate new observation types that don't exist yet and see what their impact is on the ability to predict different quantities. So that's, again, you got to trust your models. Maybe your models are or not good enough for that, but there are methods to approach that type of problem.
Good point. Yes, Olga.
Yes, hi. I may not be very original, but I think in terms of prediction, we need a near real-time data stream from critical measurements. In terms of predictability, I think there are a couple of aspects, and one of them, just my personal opinion, is that to predict this coupled system, basically you need to predict many steps of the way, starting from sun observations, and at least in my experience, your predictability for ITM systems starts degrading as soon as you start putting in predicted drivers based from the sun. So it goes back to have necessary measurements in heliospace observatory in a near real time. In terms of predictability as well, I kind of think that we probably need a combination of physics-based models with good physics, but they need to be corrected with data assimilation. And I think AI approach in certain aspects could be also very helpful because it can speed up all this process, and we will never know all the physics. And AI can kind of smooth things over and help us to find patterns. So I would think that it needs to be a combinations, synergistic combinations of all of three. And we probably want to go for conditional forecast, probabilistic forecast. It's not just an accuracy of forecast or the latency of a forecast, but percentage that's like 60% probability of this to happen or not, and I think that would be really useful. But anyway, it's a great initiative. Thank you.
Thank you, Olga. Yeah, I think I agree with you. I think that the probabilistic prediction can be very important because it's very maybe unimaginable to run all our model, the coupled models at 1 kilometer scale to capture exactly where the bubble is happening. But if you have a condition that just like forecasting tornado, you may not capture the tornado in a global forecast model, but you will be able to provide information for probabilistic forecast. So I think that's a very important point.
Thank you so much for the talk. And just something from my own perspective to share and for the discussion is that I believe there are some models, for example, you mentioned about the generative models, is purely like data-driven. We do not need to consider the possible drivers. For example, we have done something like the ionospheric TEC, global ionospheric TEC completion, which means the data source, what to feed to this generative model is only the complete global TEC maps. At one hand, the little bit challenging part is the machine learning model is very picky on the quality of the data. And as we mentioned, it's usually the case we have the limitation in the observations. And the point I want to make is there's still a lot of information unknown within the data itself. That's why the generative model, like the global TEC, by learning tons of the global TEC map, is finally able to provide some solid results in filling the global TEC gaps. It reminds me something like maybe like data or the languages. Like the languages we speak is kind of like the projection of our personal like cultural history, and a lot of the language we speak is just like a final product, is a projection. But like as we learn a language, I guess it's also a very amazing way for us to entirely indulge in such environment of the language. So anyway, just like making some like parables, like data itself, like the language itself. If we want to learn a new language, maybe it's like I go to that place, the city, and live there for a long time. That's a really great way to improve or learn the language by completely immersed in this in that environment. And a second point you reminds me is I believe the value of the machine learning model for us is to help us improve the efficiency and also help us to redistribute our attention wisely. For example, like the concentric TID, it is scarce, and if we manually to view it, it may take a lot of efforts to locate a CTID event. But with the machine learning, it will tell us, at least give us some hint that, okay, maybe in the summer, in July, that's the period of time we should put more attention to focus on that specific time period. And our attention is a very, very precious source. So that's typically 2 points on my opinion. Thank you.
Good point. So on the second point, just make sure I understand. The second point, you were saying that maybe using machine learning to connect directly some kind of source with some response, TIDs or concentric waves. That's what you're saying, instead of trying to simulate the whole sequence. Mm-hmm. Okay. Okay.
Yeah, I think that's a very important point. We have had people trying to do machine learning forecasting, machine learning application to space weather problems for nearly, I want to say about 7 to 8 years in focused manner in this field. And I think that a great way for a machine learning application for all the observed data, continuously streaming data, would be to do the categorization. Find what is important to view, find what is not important to view, and find what is something that is new. So those are like the 3 categories. If we can separate all our data into that, then we can use our attention better into figuring out how important each of these things are.
Thank you.
Yeah, can I? Yeah. So then the first point that you made about data quality being important, that's a very important point. I think that it is important that people who are developing these machine learning models work closely with the people who are collecting the data and understand like the nuances of the data. I think it's almost a drawback to machine learning is that it can be very easy to stand up a model as compared to like a numerical model, which like a numerical model requires so much time and effort, so many people, that there's a temptation to stand up a machine learning model and not being as careful as you could be, and then your model is limited by, because you did it too quickly. So, and one thing we do see a lot is, I don't know if you see this, if you go on the archive, the ARXIV, there's plenty of papers trying to predict KPF 10.7 TEC from people who are machine learning experts, like computer scientists, as opposed to people in our field. Which, it's nice that they're doing that, but I think it's maybe as a field we should reach out to those groups and provide our domain expertise because they don't understand the nuances, and I think that could be helpful. I also think, I think another consequence of machine learning being relatively easy as compared to numerical modeling is that there's a lot of like smaller siloed off efforts in our field, unlike Wacom where you have like, hundreds of people working on it. And I think it would be thousands, yeah.
We wish.
Or CSM, sorry. I think it would be great if we had bigger efforts for working on like a single.
I think it's the opposite. Now there are hundreds of people working on AI.
Yeah.
Only
but not on
2 or 3 on.
Not on the one AI thing, though. Yeah.
Okay. Yeah. First of all, I want to check how we're doing with the time. Okay.
This is from Dan Marsh. Is the most significant barrier understanding in all cases, or is it having enough data to know the initial state? So for example, a great initial condition and persistence might be better than a perfect model with poor initial conditions.
Actually, maybe I'll take that and then I'll, because I was just thinking of that, when people are talking about the propagation of the waves, things like that. I think the whole atmosphere is somewhat uniquely challenging in the case that it's very hard, we are talking about cross scale. It's very hard to separate the scales because, you're trying to predict, say, a mean state or large-scale state. But when your waves go through it, very likely will change it and maybe change it very significantly. So you almost have to get all those things right at the same time. So I think that's a big, I'm not sure if it's a barrier, but that's a big challenge. And how you do that, with a physics-based model and a good data simulation. So I think it's important to have the initial state right, but also it's very important to get the process right, and very important to get the parameterization right. Otherwise, it will quickly go, diverge and go haywire. You're end up with a very bad prediction. So it's just my kind of response to Dan's question, but I want to see if any of the panelists have anything to say.
I don't have much to add on it. I would tend to agree. Of course, I think this goes back to where I kind of started, where it probably depends somewhat what problem you're trying to address. How much initial condition really matters, or can you get away with a not great initial condition if it's strongly forced? Maybe you're less sensitive to initial condition versus if you're trying to predict some sort of small scale feature. It's maybe more dependent on that.
Oops, sorry. Anyone want to add anything?
My background is mostly observation and data analysis. So I have a question for Aussie. Recently, some people pointed out that the goal of Aussie is go back the model. And so if we end at observation, that's not actually Aussie. So I want to get your opinion and know what we can do with the model. So go back, what that actually mean.
So I'm not quite sure I fully understand the question yet. And OSSIs allow you, so really in this ensemble context, you can compute the correlation, the statistical relationship between any quantity that can be computed from the model. So if you have a particular observation in mind and you're doing cycling ensemble data simulation, you can find the correlation of any either existing or hypothetical observation with the model state at the current time or any previous time, or actually future times too, which is something related to smoothing. So there is lots and lots of information available. That information comes from the model. And so if the model is inaccurate, then that becomes disinformation rather than information. And I think really the trick is understanding the limitations of your model when you're evaluating what it tells you about the value of certain observations and how they're related to the state, both in the past and in the future. Did that help? Yeah, go ahead.
I would just make a comment. I think there's sometimes a different nomenclature what people use for Aussie in sort of our community versus, say, for weather prediction. Often I think in our community people will say Aussie, you just sort of sample the model and get some sort of synthetic observation, and then that's the end. You're just saying, well, this is what my observations would look like, but you're not really going back to how that will impact a forecast or prediction. And I think that's maybe the part that is missing often, is we just generate some synthetic data, but never link it back to how that would improve a prediction.
I'll go with Fabrizio and then Larry. Oh. Oh, okay. Then Fabrizio and then Larry. No, you want to go or, okay, go.
Well, my comment is at different area, but if you are continuous this topic, you can go ahead.
Okay. Yeah, sort of related to what Guiping was saying. I've seen attempts to use machine learning, artificial intelligence to create observation or fill in gaps in observations. I'm worried, but you know, that's probably something that is going to happen more and more in our field.
Ben, you have anything to say about that?
Yeah, just while we're negotiating, my quick comment on that is there's a long history of trying to assimilate things like analysis products or other process data. This would be analogous to that. And the real challenge is characterizing, you get correlated error structures in those products. I think you're aware that that can be a real challenge to knowing what you can really get from those things. I think very valuable, but it requires careful thought.
So who's next? Okay.
So just building on that, there have been quite a few studies, the lower atmospheric studies, where they have used machine learning to understand the sensitivities of the system. So for example, if we know we want neutral densities to be forecasted, not everything in the lower atmosphere is going to be affecting the neutral densities that we need. So probably one gap that machine learning can definitely fill is to identify what's most important if you have a defined goal. So just a thought.
Okay. Now we go to Larry.
I just sort of wanted to clarify what your interests are in the sense of, like, during these last two major storms we had in 2024, there were big auroral disturbances over the continental U.S., right? Mm-hmm. Big magnetic field decreases and all sorts of excitement associated with that. Are you interested in that kind of a thing? And if so, I mean, that gives the large magnetic field depressions on the ground that cause all sorts of DBDTs and, you know, a potentially major contribution to space weather. And they're associated with these flow channels that come in within the auroral oval. In this case, the auroral oval, you know, gets really to low latitudes. And it, you know, it's coming in from the polar cap. So if we, one, as Ashley was saying, we want to try to understand this, the connections and what is driving this thing. If you want to predict it, you got to first figure out what it is.
Yes.
And so are you interested in that? And how to measure what's going on. I mean, like, these things come in, they cause the big magnetic field perturbations. They give you, you know, penetration and shielding electric fields that are tremendous and, you know, jump the ionosphere of the equator by a huge amount just by one of these things coming in. So are you interested in trying to predict those things? You can't do that with any of these models right now whatsoever. You can't do anything with resolution or AI or anything like that unless you can start to get the physics of that involved. So, you know, and you could start to make progress on that by using, you know, capabilities of the two-dimensional flows you can get from the SuperDAR radars now. You know, maybe expand the coverage of the SuperDAR radars to cover more lower latitudes. You know, and also the TEC measurements really help a lot. You know, even ASIs could help, but that's hard to get that kind of coverage. So I was wondering if you're interested in that kind of thing and whether you want to include that in your discussions and thought processes.
Yeah, actually, in my introduction, I did mention that, you know, the driver is a very important thing. I think the reason today we're a bit more focusing on the system, the response, is that we felt that our colleagues at Shine and GEM, they should tell us what the driver should be. So that's a predictability problem of the whole system. Definitely will engage, you know, will involve collaborations with colleagues from those communities. But
some of us are here.
Yes, that's right. So yeah, I think for the whole space weather, of course, the storm time space weather is a big part of that. Maybe what we have talked so far is more on the kind of response side. You know, when we get a forcing, you know, either through using some empirical model or AMI, or, you know, a first principle model like MAGE, how our system will respond to that. So maybe we're now focusing a bit more on that. But how to best specify the driver is definitely a very important part of this whole chain.
I guess what I was saying would be specifying your driver in the sense of what you're talking about.
Mm-hmm.
And the big major drivers.
Yes, yes.
That's my thought.
That's right. Yeah, I was thinking that even we get the driver, right? So for example, the May storm last year, not the last year, the 2024, we may not be able, different models may behave differently, but we may not be able to, for example, produce those big swirls in the north and the southern hemisphere. So that would point to some issues, maybe both the driver and how our model is responding to those drivers. So exactly what's broken or which link we're not doing correctly, that's a big, interesting question we want to look at.
At least integrating in with the ground-based type observations like ASCII was talking about.
Maybe ASCII you want to
physical connection might, something you could add that's within the scope of CEDAR by itself.
Yeah, I mean, I think there is we talked about it would be great if we can have all observations at all points and on the Earth, right? But that is that is an ambitious task, which is an understatement. But what we can do is, I think Hanli also mentioned in the beginning, to have observations at strategic locations. The strategic locations to be determined, but for example, the meridian chains. We have seen latitudinal changes, of course, of variability. We have seen longitudinal variabilities, but how do we combine that too? Can we create multiple meridian chains of instruments combined with some latitudinal coverage for, say, polar cap, for auroral zone, that allows us to both characterize the drivers and then understand the geo-effectiveness of these drivers. So drivers, we can characterize the drivers, but our field is also concerned about how those drivers are impacting our systems, and that is the geo-effectiveness of any of these things that is at least coming from outside the Earth. So that is where we are concerned about predictability as well.
Hi everyone, I'm Hui Shao. I want to introduce a little bit my background because it matters to my comments here. I joined NRL for 1 month, and for the past couple of years started working on space weather data simulation. And prior to that, I'm 9 years or more than 9 years data simulation system development, which is CEDAR for NWP. So the first question that came was, gosh, you don't have a lot of observations to assimilate. And there's a lot of uncertainty evaluations in terms of model and the observations. It's so far behind NWP, and I felt it's challenging. So I certainly agree with the comments from panelists mentioning about, for the model side, observation side. And I feel there's one question here, what are new observations are needed? Or that's my first question is, because I'm also working with a working group, which is interfacing with the coordinate group for the satellite missions. This is from agencies from the international community, and I heard very limited voice from space weather people. So basically, it's mostly coming from NWP, and I feel, people here, you need to talk to your agencies to pass that voice to this kind of high-level coordination for the international missions, because promoting observations sometimes not only having the voice stay with the scientific community and going to higher level is very important. And I feel, evolving into this kind of community work would be very helpful to promote space weather observations. NWP did a great work, and now it's our time to promote space weather observations. And second one is probably is a more question, what's the barrier for barrier? So with the existing observations, I felt difficult to get enough data for my research. And it's all over places. I had to adapt to different formats, different websites to download data, and it's limited. So maybe my question is here is asking, what's the barrier for getting the data? I heard continuous streaming of observations. Then what's the barrier behind to stop doing that? To do that among this whole community? Why even within community is difficult? Because the NWT has, of course, high-level cooperative agreement among countries to share data through the GTC service. And among research, there's different data centers to have archives of retrospective data. So what happened, why we don't have something like this for the space community? Maybe I'm too new to know there is such thing already. But I would like to emphasize, I just feel as a community, this is a great place to organize something like this so that we can get easier access to data, so that we can, improve our extraction of information from observations, not just assimilating retrievals, but we need to go to a low-level data to get more information to help models validate, not analysis only, but validate what models' behavior. That's important. So observations are the key for training, for model development, and I think this is probably the simpler question here to get the community work on something. Have a unified platform, more or less, to get the data to people. So that's my comment and question.
I mean, yes. Yes to all of that you are saying. And I think as a community, we have been trying to develop something. To me, I call it getting our house in order. We have all this continuously streaming data, but we do not yet have a way to provide data that is, say, cross-calibrated, data that is standardized, that adhere to specific data standards. And few people within the community have been working on that, but we have really not got anywhere just yet. It's a hard problem. It's a hard problem because our community, especially, I'm talking now from the ground-based community. I think NASA has the SPDF and the way to provide more standardized and version control data products, et cetera. For the ground-based community, things have been a little more left to the individual PIs, and so there is an organizing that needs to happen. Well, yes.
Anyone else want to comment? Oh, yes, John.
Is this on? Okay. I'll keep this brief. Just some general sort of impressions or suggestions, if that'll help. First, going back to some of the discussion earlier, there was discussion about quantification of uncertainties. There was a joint NSF-NASA program through the Space Weather Program about 4 or 5 years ago, dedicated to quantification of uncertainties for space weather. I believe it focused primarily on solar and mag and maybe heliospheric processes. I'm interested to know, and we can talk about this later, or you can answer offline, but how many people in this room were involved in that or aware of that? And my sense is that this, the upper atmospheric physics and the sort of the CEDAR type community might not have been as involved. We should look back at that, see if there's lessons learned, see if there's things we can take from that and maybe even revisit that. But I just wanted to make people aware that there was that effort. We talked a little bit about going back to and looking at how numerical weather prediction community is operated. And excuse me, one of the big breakthroughs in forecast skill, from what I understand, and I could be wrong, but when the availability of hyperspectral imagers for IR and the ability to assimilate radiance directly into NWP, systems, the model and DA, that was a big leap forward, so to speak. We kind of need that for this community. One possible way would be, okay, we have so many more things in low Earth orbit now. You know, there's been a lot of talk about, can we put just a density or an accelerometer on each one of those? We need something like that, something that will push things forward, massive amounts of some kind of data. All those space-based observations are great. It's a challenge to take all that disparate data from, and try to assimilate it. We're going to need something else. And I think the biggest problem is the thermospheric density variations problem, day to day, hour to hour even. So think about that. The last thing is, again, I'm not exactly sure how these work, but for the grand challenge, for this group, for this community, for what you've been working on for the last, was it 3 years? Is that what the grand?
This grand challenge?
Oh, this is the start. Okay.
This is start.
So when you start, I think about what the community's achieved to date. And Nick, I don't want to put you on the spot, but when you said, you put that comparison figure up from your 2014 paper, and then you said, okay, we did that today, we might see some of those same biases. That's, you want to show what sort of progress has been made to date. I think a lot has. You want to show what you can do probably in the 3 to 5 year time frame to advance things, especially for prediction. That's what we're talking about. And you really got to hit on what are you going to need. And if it's ground-based to support space-based, if it's critical infrastructure in terms of computing, resources, people, technology, that I think is where you would help to organize this stuff. And there's a lot of different threads. I'm just kind of encouraging from an outside perspective how to pull these together and focus a bit, but I don't know. I think going back to that quantification of uncertainty would be a really good place to start.
So I'll jump in here. I was a co-I on one of the SWQU initiatives that was actually led by Aaron Ridley. Most of them were directly associated with model development, and actually Aaron's one developed a new replacement for GITM called Ether, and we developed hand-in-hand the data assimilation, the ensemble data assimilation, to do the uncertainty quantification with that. And just shameless plug, that system is mostly completed. The data assimilation system works, and so far no one's used it. So it is a great opportunity for students and other people to address exactly the issues. And then quickly on the NWP, I think your assessment was essentially correct, and that is that there's work involved in basically every single type of instrumentation at the end of the day to put it into a predictive system with data assimilation. So there's idiosyncrasies, there's things to be learned about each type of instrument. If you can get a particular type of instrument that has very dense, lots of observations, then you can get a lot of information fast from that, as opposed to 65 different types of instruments, all of which are really cool, but it takes a huge amount of work for each one. So I think that sort of focus, it's related back to what is the problem you want to predict, and then finding an instrument that has a lot of information about that.
Yeah, and the uncertainty quantification with instrument data, that is an ongoing challenge. Not only in uncertainty quantification, but how the uncertainties on one instrument relate to uncertainties on the other instrument. The cross-calibration of uncertainties is it's multiple student thesis, I would say. It's not a trivial problem, and not only is it not a trivial problem, but I think it would require, like you mentioned, an actual funded initiative to do this in a systematic manner, because that also goes hand in hand with what information we can provide to data assimilation models. And right now, for instrument providers, it's a challenge to make sure that the interpretation of the data is correct, and that is not easy. But that sort of initiative is, I think, needed. And to Jeff's point, it is important that when we try to develop networks, networks of homogeneous instruments are really important. We can have multiple heterogeneous instruments, but each instrument network should be working similarly, same, so that you can provide calibrated quality, same data product across. And so that, I think, helps a lot with assimilation.
One sort of follow-up, having sort of built the data assimilation system for space weather, we have been fortunate at times to get some funding for one postdoc or something to work on, say, gold data assimilation. But even then, it takes them a long time to put in one instrument. So really, when it's only one or two people working on this sort of thing, you can't bring in all sorts of diverse observations that are different format, different thing, different errors. It just doesn't work in any sort of quick time. So some sort of uniformity for data assimilation is kind of critical, especially with sort of small numbers of people working on these sort of problems.
Okay, thanks. Oh, yes.
So comment, just a little bit of a different perspective. I agree, and what it's going to come down to is scoping the problem and really focusing, and that's been a common theme here. But if you look from, I'm going to go from an operational usage point of view. What we've found is a lot of things that are used operationally for predictability, the models and all, they are driven, of course, as we know, by solar indices, KP, F10.7, and a lot of what we're finding is the majority of the error is due to the error or misunderstanding or in those variables, not the fundamental physics, in those operational systems. I would actually almost want to challenge, we either need to have something better to base or initialize our models on, or we need to improve those type of indices and all. I don't want to say before, but I want to say in parallel to better understanding the physics and doing new models and new AI and ML from a end user perspective, not from a science understandability.
So what you're saying is we need a higher quality driver data.
Higher quality, more accurate drivers.
Okay.
So I think these last two comments were a great segue to this next activity, which is going to be group discussions on key science questions and what the group collectively can do in the next 3 years. So before we do that, let's thank the panel one more time.
Okay, thank you everyone for joining us today, engaging in the lively conversations, and we're gonna slowly start to transition so you can share out from your groups. I know it's a lively conversation, but we're just limited on time, and we'll try to kind of bring this group back together in next CEDARs and in other occasions. So, and maybe Jian, if you want to come and talk about what you guys talk at your table, or do you want, I'll get you this.
Thank you, Yaga. So we went through the discussion of the drivers. So basically is, so it's the first one, and I think the most important message, like a little bit high level message we got from the group is how can we define what is the accurate characterization of the drivers. So to what extent we can say the drivers are well kind of captured. For example, from magnetospheric forcing, we do not have the very nice global and continuous coverage of all the aurora activities and convection, ion drifts, convection patterns. So with the existing capability of the data, how well we can do and constrain the driver from magnetosphere, and also the energy band. For example, aurora particle precipitation, we are good with a few keV to 30 keV, but we may not be able to measure lower energy. That's important for for some phenomena like SUPs. And so this is also something that currently is not totally fully resolved. And then we also discussed things from the lower atmosphere forcing. So are we looking for the good prediction or predictability for regional or for global? And how good is good enough? And not only driven by what? You wanna?
When we're approaching the problem, yes, we need to know what the operational or end users need right now, and we should be working towards that predictability. But we can't just be chasing after that. You also have to anticipate, because the technology and the end user needs are constantly changing. So if you are addressing what the needs are right now, you're going to be behind in 5 years. So we need to have parallel efforts going on to improve predictability or on multiple scales, short-term, mid-term, and long-term.
Yes, and one more point is we also talk about getting inputs from other communities. For example, solar communities, they may have better indices to represent the drivers. So can we collaborate with them to improve the driver? So I think my feeling is we are kind of still confused. Maybe not confused. Maybe it's when we want to ask ourselves is really to what level we are kind of satisfied with ourselves, with the existing capability, and maybe future mission as well. So so that's what we have.
Maybe not confused, but maybe these working groups can help us kind of refine it and get some of the questions you're asking if we start to form it. Thank you, Jian. If you want to go, Hui next.
All right. So our table actually end up talking about two major points. One is more coming from the operational needs, because we do have some agencies working on extending the models from lower bottom troposphere to the upper levels, and the communication cross agencies or sectors about the model extension, and this kind of collaborations are definitely appreciated, and we went over to that direction a little bit more. And the other one is coming to the observations. So rather than repeating why we need observation, etc., we actually come back with 3 action items we thought we could propose. The first one, we recognize that actually for NWP, there was years of study to build up some standard. For example, radio sound is more or less trusted to compare with models, compare with the other observations. And RO, radio occultation observations, is another one because it naturally has limited biases. So, but we feel the first item for the community could be if we can have a collaborative effort to establish a baseline observation measurement or instrument we can use, and we can more or less validate our observation informations across different types, measurement, missions, etc. That will give us a lot of confidence or a baseline type of knowledge about what we can get from observations. So that's our first action item we think maybe we can do. The second one is we also feel like in this community we have limited voices coming from data providers or processing teams, or even there's no commercial vectors. And I want to say is, I'm organizing other meetings, which is for radio occultation. We have data providers coming in, and they are very helpful because they can tell us what's the problem in their data and how we can assimilate, use them to validate. And open such a pathway would be very beneficial to a scientist here. So our second action is we would like to, if we can, invite data providers, processing teams, commercial vectors, space industries to come to this community to give us talks, talk with us, and we can, even in the working group, we should open to them. So the third one is cross-sector, cross boundaries kind of conversation. And our team is mentioning that it would be great even just at the starting point to talk with each other. Maybe each agency has different funding mechanisms or different focus areas, we can start with abstract or more generic areas and then we narrow down to certain topics. But starting with like people from different sectors talking about AI, ML efforts, we know each other, what you are doing, that's the first step. So really we propose to start with generic areas, not too specific, but we can going to narrow down certain areas. And we can, data people you can also jump to teams to know what the other group doing, right? You know what the data are providing now, and then later we can form different working groups. So that's our third recommendation.
Thank you so much. So Anna, and maybe because we're running out of time, the other three group, we can have a pointer or two of the highlights of your conversation. That would be great.
So in our group, we had a lot of discussion about model validation and comparison of different models. That when, in order to improve predictability, obviously we need to do comparisons across different models and understand what is the result of the drivers to the model versus what is the result of the model itself. So to make sure we're doing apples to apples comparison, and that we have the data types available to do all types of the type of validation that we want to do. So that data availability can be a big limitation in that. The other thing that a number of people mentioned is that if you're trying to use a model you're not very familiar with, that can also be a big limitation, that it can be difficult either to get access to the data you need to set it up or to the information in order to do that. So just to make sure that we have everything we need in the steps to make it easy for people to do comparisons and possibly to choose an event for many people to look at together.
That sounds great. And Ling, if you want to share a few notes.
Okay, so our group, we started our conversation following that question about the data. Even with available data, it's kind of difficult to use. So we want to say that all NASA mission data are archived. So we have NASA has SPDF database and there's a Magical database. So we want to everybody to know this database, data source, and to make the data easy to use. And then we move on to the driver. So our students member says we need to have more tutorials on student day on the drivers, on the IT science in general. And we talk about the forcing solar, for the solar EUV, we need to have increase the temporal resolution and for the solar flare and spectral resolution. This is mainly for the lower, like XUV part. We are not spectrally resolved. And for the solar wind and magnetospheric forcing, we need to resolve mesoscale forcing better. And then for the terrestrial weather, our day-to-day weather from the low atmosphere. So we know that high resolution model can resolve more waves. However, it's not very feasible, in terms of a predictability. What's more feasible maybe to use like AI, machine learning to improve parameterization. And for the response, we need a two-way coupling between thermosphere and ionosphere. And for uncertainty, when there is uncertainty, we still need to understand where the uncertainty is coming from. Like, is it forcing uncertainty or internal physics? And how uncertainty may be different for different models.
Not really, no. We didn't, so sure, I will try. We talked a lot among the group about the drivers and the uncertain, or the predictability aspects. We didn't talk about the response as much, but I just saw it there. And the question about background conditions, cross-scale coupling pathways, regulating the response of the IT system to external forcing and shaping space weather variability. Well, to me, the response is, a lot of it is this question of you dump a lot of energy into the system responds. The changes in the thermosphere and the ionosphere and the changes in the currents can actually feed back into the magnetosphere. That's an important question. But just generally speaking, the big challenge, I think, has been how do you get proper two-way coupling between, in your model of the thermosphere and the ionosphere. The ionosphere usually drives, you create a thermosphere, from the drivers. Energy gets input, the system changes, but then what's the follow-on and what's the feedback? And I think the big question and the big thing that some of our efforts through NASA and the Space Weather Centers of Excellence and other things, people who are actually trying to develop these coupled systems to include, what is the upper atmospheric response and space weather, that's a stumble. That's a hurdle. And so I just thought I'd throw that in there. So I threw it in at the last minute without talking about it with any in the group. So apologies, but I think it was worth noting.
Thanks for sharing that. Yeah, so I know we're a little over time. We have only one group left, and then I'll finish up with some information about the afternoon session.
Okay. We also talked about data. Of course, we recognize, the sparsity of the data, but also we recognize at CEDAR, we are pretty much a research community. And so it's very important to use this, whatever resource becomes available, maybe from NSF, to use that strategically. And that may be a good place to do kind of Aussie studies. What's the best way to, place your observations, or what kind of observations you want? So that's one thing. The other thing is that we thought for the meteorological community, one thing they can one advantage is they have a lot of data points. They release balloons or radio sounds every 6 hours or something at millions of places all over the world. The key is that they have very cheap set of instruments. So how to for our community, and maybe if we have a conversation with commercial entities, to convince them to have a cheap deployment of cheap instruments, like GPS, maybe can convince the ship fleets to put GPS on their on their ship and give us data, share the data. They already did, but maybe how to, maybe that's one conversation they can have is how, in what way they are willing to share their data. And that's the second thing. The other thing is that we are limited, kind of data poor, limited by data, but there are AI techniques, Richard mentioned, that can be used to deal with, small data set kind of systems. So maybe we should explore that and exploit that. So I think that's all the things we talked. Did I miss anything?
Okay, thanks everyone. I just want to say thank you for joining us, staying for the panel and this part that required group conversation. Sometimes it's hard when you're at a conference to put that time in, but this was great, really appreciate it. And just to let you know, as a follow-up, all the facilitators have been taking notes, and we're going to take this into account while we form the working groups to see what were the interests that the community had. What are the areas they want to work on? And we had your names taken so that we'll email you out, and hopefully if you're interested to keep engaging with this grand challenge, we can work with you. And just as a reminder, we have an afternoon session, which is a similar format. We'll start with a panel discussion. This would be more of a cross-sector panel discussion, and then a similar group conversation afterwards. So thank you, and sorry to keep you from lunch.